In this video, I'm going to show you a function that is a smooth function, but it's not an analytic function, which means it's not equal to its power series. So, definition here. Analytic function means equal to its power series. And of course, by power series, I mean Taylor series. Okay, so the function in question, let's just get it right there. I'm going to work in the reals. The function is given by, well, it's 0 if x is less than or equal to 0, and it's e to the minus 1 over x if x is greater than 0. And so this is defined for all x in R, real valued x. So first of all, let's figure out what its Taylor series might be. Well, an easy way to find that is to use the Taylor series expansion. So call Taylor series for f is centered at x naught is, well, it's this sum. It's an infinite sum. I take n derivatives at x naught, divide by n factorial, that's the coefficient, and then the series power looks like that. And the thing to notice, of course, is, notice f of x is greater than 0 if x is greater than 0. Why? Because e to the x is greater than 0. And it's equal to 0 if x is less than 0. So if we choose a center to be less than 0, anywhere less than 0 will do, the Taylor series for f is all zeros. But f is not. All 0. Okay, and of course if I were to center on the other side, center for something x greater than 0, there's a theorem that says that a Taylor series can't be 0 on an open set unless it's entirely 0. Really a property of the same thing. Okay, so f, as I've written here, is not analytic. Okay, now of course there are lots of functions that are not analytic. What's perhaps surprising is that this function here is smooth, which is to say all of its derivatives exist and are continuous. I mean, you could certainly have a function that's not analytic because it's discontinuous. That would be unsurprising. But this function is smooth, and so I will show that to you now. So now, to establish that f is smooth. Well, first order of business is to show that it's continuous. I think the thing to note here is that if I were to take the limit as x goes to 0 of f of x, that needs to be equal to f of 0. That's the whole point of continuity. That's what we would like to show. Now, the thing to realize here is that that's really the only place where anything can go wrong. The function that's constant at 0 is certainly continuous, and all of its derivatives exist. There's no problems there. And e to the minus 1 over x is also continuous, and all of its derivatives exist for x greater than 0. There's no problem there. The only problem is where they join up. So I want to show that, in fact, this limit exists. We're in the real numbers for the moment, so that means that the limit from the left and the limit from the right need to be equal. Here we're having some pen problems. Limit from the left and the limit from the right of f of x need to be equal, because if they're not equal, then there's no hope of them being equal to the same thing. Now the limit from the left, this is just the limit of a whole bunch of zeros. So of course that's 0. So we need to show that this thing is equal to limit as x go to 0 from plus e to the minus 1 over x. Now, at least notionally, if you look at this, you say, well, x is positive going to 0, so 1 over x. It's going to get really big. It's going to get really big and negative. So this really looks like the limit as y goes to minus infinity of e to the y. Of course, that's 0. All right, continuity is established. It's helpful at this point to draw a graph of what the function looks like. The function is non-negative. It's 0 here, and there's positive on the other side of the axis, and it has a limit of 0. And it kind of looks a bit like this. So this is what y equals f of x looks like. And so really all the activity is right here. Now, it's helpful for the rest of this calculation to spend some time being a little bit more careful about this equality right here. And the way to do that is actually by way of using some logarithms. So let's re-examine that. Re-examine the limit as x goes to 0 from above. And we're going to use logarithms. And in particular, if I take the logarithm of the limit as x goes to 0 from above of anything, but certainly this function here, it's equal to the limit, then the logarithm. Now why is that? Why am I allowed to exchange the limits in the logarithm? Well, the reason is because log is continuous for all x greater than 0. All right, and by studying what the limit of the logarithm is versus the log of the limit, we can kind of reverse engineer what's happening based on the fact that we know what the logarithm does. So here, let me give you a quick reminder sketch of what a logarithm looks like. This is y is equal to log x. So if I have something that is going to 0, it'll make the logarithm go to minus infinity. So note the log of x as x goes to 0 from above is minus infinity. And that's the only place where that happens. Okay, well, given that little side note, we can also do some algebra. The logarithm of e to the minus x is, of course, minus. There we go. And what does this number do? Well, as x goes to 0, the denominator goes to 0 in this fraction. It's going to go to plus or minus infinity. And of course, it goes to minus infinity. So conclude that since this limit is minus infinity, limit as x goes to 0 from above of e to the minus 1 over x is equal to 0. Okay, now of course that seemed to be just a waste of time because we just got that earlier by this argument. Fair enough, but this helps with the derivatives. Because remember, what's the name of the game? The name of the game is to show that this function here is smooth. Limit from the left is equal to limit from the right for all the derivatives. So we want to take derivatives on the left. Derivatives on the left are all supposed to be 0. Derivatives on the right are going to be more complicated functions involving these exponential functions and such. We're going to apply the logarithm to them to kind of simplify that. Okay, so let's do it. So, goal, since the limit from the left of all the derivatives of x are 0, need to show that the limit from above, i.e. from the right, is equal to 0, 2. Okay, so let's do that. So let's start by taking one derivative. Well, this is elementary enough. This is a chain rule kind of problem. So I'm going to get an e to the minus 1 over x times the derivative of minus 1 over x. All right, so there it is. So you could say this is something looks like this. Now, of course, this kind of fraction looks like, oh, I could just take a limit of this, right? No problem. I want to take x going to 0 from above of this fraction, and immediately run into problems because it's 0 over 0. This is an indeterminate form. And unfortunately, L'Hopital's rule would be the sort of thing you'd want to do, but L'Hopital's rule fails. Why? It's not that it's false. It's that it doesn't help. Because when I take a derivative of the numerator, it kicks out a whole bunch more fractions that ending up more x's that end up in the denominator. And although I do get to clean up some of the denominator, it just doesn't help. So we want to do something else. And the thing to do is to actually use these logarithms. So strategy. Let's take the log of the limit as x goes to 0 from above of this quantity. Now there's a little bit of a problem here. That being x is positive, e to the x is positive, and I'm going to be taking the logarithm of a negative number. Okay. Well then, let's just show that this guy is 0. Or rather, since we're after this being 0, I want to show this is 0. The extra sign does not change anything. So we'll happily ignore that. Okay, now of course, since the logarithm is continuous, we can go ahead and do our little exchange. no problem there. And of course, do our little computation. And we get something like, well, the minus 1 over x that we got before. But now we get something else. We get a minus 2 log x. Okay, well, that is what it is. And so the question is, well, what do we do with this? What's the limit of this thing? Well, you put in a 0, and the first guy, try to put in a x going to 0 from above. This guy goes to what? Well, I guess it goes to minus infinity, as it did before. No problems there. And the logarithm, on the other hand, this guy, as x goes to 0, this guy goes to minus infinity. But I got an extra minus sign, so this goes to plus infinity. So I'm left with still an indeterminate form, but instead of it being 0 over 0, it's minus infinity plus infinity. Still indeterminate. Okay. That's not really the end of the world, because what we can do is we can, well, put everything on a common denominator. That, of course, won't change anything algebraically. No problems there. So we'll have an x in the denominator. We have a minus 1 up here. We have a minus 2x log x in the numerator. All right, fair enough. It's easy enough to check that, well, what happens when x goes to 0? Well, when x goes to 0, that denominator goes to 0, of course. But what about the numerator? Well, we've got this x log x business going on there. What happens to x log x? What happens to x log x? Okay, well, let's peel it off as a separate problem and kind of examine it on its own. The limit, as x goes to 0 from above, of x log x. And you look at this and you say, well, gosh, I've got x going to 0, and I've got x going to minus infinity. Right, this goes to 0. And this guy goes to minus infinity. So yet another indeterminate form, this one being a 0 times infinity kind of indeterminate form. Oh, gosh. But this one actually we can solve by L'Hopital's rule, but again, a little bit of an algebra trick. How does that work? Well, what you do is you throw the x into the denominator. Of course, the x isn't in the denominator. It doesn't really want to go there. That's okay. I'll make it go there. Now, what do I have? Well, I have a minus infinity on the numerator, and guess what I have on the denominator? Another minus infinity. Still in indeterminate form. Finally, after a whole bunch of false starts, we have a use of L'Hopital's rule that actually works. Actually works this time. And let me take a derivative of the numerator. The derivative of logarithm is 1 over x. Derivative of the denominator is a minus 1 over x squared. Oh, but now there's just polynomials in sight. This is something we can actually handle. And I end up, let me rearrange matters slightly. Oh, x squared over x as x goes to 0 from above. Gosh, that's going to be the same thing as the limit of x going to 0. Okay, that's just a plain old 0. Okay, cool. Now, we can use that fact here in the green box. So, let's go grab what this was actually from the beginning. What was that? This quantity that we were trying to compute was the limit of the first derivative of f. Limit, or rather, even more so, this was the logarithm of the limit as x goes to 0 from above of the first derivative of x. That thing was the limit as x goes to 0 from above of this quantity here. Which quantity? This one. Grab it and put it here. And now that green box is helpfully reminding us that we're going to make use of what we just learned from above. This is really minus 1 over x. So this whole works as minus infinity. Oh, and so the limit as x goes to 0 from above of f prime of x must be 0, taking out the logarithms. And we can say f prime is therefore continuous. Now at this point you're probably saying, gosh, that was a lot of work. What about f double prime and so on, all those other derivatives? Well, actually, here's something really cool. Notice that f double prime is going to be something that looks like an e to the minus 1 over x times, well, stuff, polynomial stuff. In particular, times a rational function. And the point is that the calculations we just did with the logarithms are basically going to come out the same. We'll end up changing the 2 with whatever degrees we're dealing with. So this 2 right here in the green box will end up changing. This does not end up changing. And so we can safely conclude that fn of x continuous, i.e. f is smooth. Now, what this means then is we have a smooth function with no power series. Now, you might say, all right, this is some stupid counterexample. And to some extent, I suppose it is, although I have another video wherein I compute the Laurent series, the e to the minus 1 over x. Not analytic, but it is analytic nearly everywhere except the origin. The place where we spent all of the effort in this video, looking at x equals 0, is actually a spot where analyticity fails. Yeah, we know that. We just showed that. And as a result, you can write a Laurent series centered there to kind of take up that slack. You don't end up with the zeros along the negative real axis, but that's fine. But in any case, is this a silly counterexample? The answer is no. This is really the first of, this is called a cutoff function. F is a smooth cutoff function. And there are lots of these. And if you make, take f of x times f of 1 minus x, you end up with a function that looks a bit like this. At 0, it comes up smoothly and then goes down smoothly. I suppose I ought to highlight this guy in blue. This is called a bump function. And bump functions are really handy. They crop up in many places. They show up in splines, which are great for doing art. They're good for doing fonts. They're good for doing statistics and fitting. And they're even good in solving differential equations too. They're so important that actually splines don't always exist if you have a space that kind of looks like plain old Euclidean space. And they're so important that we make use of a special property to force them into existence. This is called paracompactness. And paracompactness implies, after a lot of work, bump functions exists on manifolds. And that turns out to be really important. And paracompactness is often a mysterious property in the definition of a manifold. And so if in the future, if you run across that and you say, why is there this weird paracompactness or a slightly different condition? It's called second countability. The reason why that's there is to make bump functions exist, and the reason for that is so that you can have all of these wonderful things like splines and such. But really, ultimately, what it means is it means that you have functions that can be smooth but not analytic.